let's go to the last presentation of this session this morning. We have Dr. Ben Itzstein from, I think, CSIRO to give a talk on the structural health monitoring system for the Sir Leo Hielscher Bridge. So I hope, Ben, if you are ready, please start your presentation. Thank you.
Hi, Tuan. Thank you for that. I'll just share my screen. This looks good.
It's Rossi. You just might have to move your microphone closer to your mouth so we can hear your low-level sound.
Sure. Can you see my screen?
Yes, thank you.
Perfect. Thanks for that, Tuan. And I think thanks, Mujtaba, for answering the probably same question I would have got at the end of this presentation. All right. Good morning, everyone. I'd like to thank firstly Professor Tommy Chen and Dr. Lei Hu for giving us the opportunity to present to you today at this 12th ANSHM annual workshop. I'm Ben Itzstein, and I'm a software engineer at CSIRO's Data61, and today I'll be sharing the presentation duties with Dr. Khoa Nguyen, a senior research scientist also from Data61. So we work in the transport analytics group at CSIRO and have been leading the development of a structural health monitoring platform for the original Sir Leo Hielscher Bridge, which is part of the Brisbane Gateway Motorway. The original bridge is actually the one in the foreground here. So our group has actually been working in structural health monitoring for almost 10 years now. Particularly Khoa Nguyen has been doing a lot of research in this area. And here I've just shown some of the key SHM projects that we've developed over that time. A common theme that pervades all these projects is typically the use of domain models combined with machine learning, sort of similar to some of the hybrid models that have been mentioned in other sessions over this workshop as well. For example, in the Sydney Harbour Bridge, we instrumented around 900 jack arches along one of the bus lanes of the bridge, which was a repurposed tram lane. Obviously, the Gateway Bridge, we've just done some instrumentation on other bridges, water pipe failure, and some also complex system analysis as well for system failures in HVAC, robotic arms, as well as some kind of implied sensors as well, using road surface monitoring as well through onboard sensors. But today we'll be focusing on the Gateway Bridge project. So for those of you who don't know it, this is the Gateway Bridge. We've developed a pilot system which is still being refined and improved, but is a real system on a large scale infrastructure that we want to give you an initial sense of. And so we worked with a consortium of partners to develop this SHM system, including Transurban, which is the asset manager, University of New South Wales School of Civil Engineering, Civil and Environmental Engineering. They did some of the structural modeling with us. Cisco and Innovation Central provided the communications and edge compute hardware. And Rockfield Technologies, who we worked with on the sensor instrumentation and the data acquisition. And we were actually honoured to be awarded the Smart Transport Infrastructure Award a couple of weeks ago by ITS Australia for this work. I think it's good recognition for the value of structural health monitoring to the ongoing management of important critical public infrastructure by the industry there. So just a little background on the bridges themselves. Better known as the Gateway Bridge, the Sir Leo Hielscher bridges are a pair of concrete cantilever box and girder bridges. The original bridge was built in 1986 and had a typical daily design volume, of 12,000 vehicles per day. The duplicate bridge opened 24 years later in 2010, and it had a design life of 300 years this time, now serving over 110,000 vehicles per day. So we were tasked by Transurban to do a pilot instrumentation of the old Sir Leo Hielscher Bridge at a critical section of the bridge around about here, where there's a lot of braking forces on the bridge deck as vehicles are heading downhill in the northerly direction before they're exiting. So the whole bridge is about 1.6 kilometers long, and the area of each of these spans is 70 meters. Yeah, so this bridge is actually geographically located, it's crossing the Brisbane River and is near the Brisbane Airport. So maintaining aging transport infrastructure like bridges is challenging, and obviously the original bridge I don't think was designed with a 300-year lifespan. So adopting a condition-based maintenance approach using structural health monitoring was something that the asset manager identified as a good way of improving the productivity and safety of their bridge inspections and the overall asset lifetime. So today I'm just going to step through at a fairly high level some of the different components that that make up this end-to-end system that we've deployed. There in the bridge environment, there's the sensing capabilities, and then we have communications with a cloud-based structural health monitoring platform consisting of the processing, data management, analytics, and some end-user visible applications as well. And some of the different sorts of insights which you guys would all be quite familiar with are things like anomaly detection, structural changes, the opportunity to inform predictive maintenance, and have some confidence in your asset inspection accuracy. All right, so I'll go through the sensing through data management parts, and then I'll hand over to Khoa afterwards. So as I mentioned earlier, we've instrumented a critical 71-meter span of the Hielscher Bridge, which is near the exit ramp. And we've installed over 60 different sensor packages on that span, including accelerometers, strain gauges, and thermistors, which allow us to monitor vibrations in 2 dimensions, along with temperature, shear, and bending forces. We've also got access to some pre-existing data sources, the CCTV footage covering the road, as well as tolling information. So this allows us to characterize some of the loads which are passing through the instrumented span. I should mention that it's a 6-lane span, which is conveying traffic exclusively in one direction towards the north. And here, this is a 3D model which was produced by Rockfield to give some spatial awareness of the sensor placement. It's quite periodic. As you can see, we've sort of instrumented periodic sections of the span. These 2 hollow boxes are naturally supporting the bridge deck above. So there's a combination of the different sorts of sensors I mentioned before, the 60 sensors or 60 plus sensors. Now, fortunately, we're working in a stable, sort of benign environment within the hollow of these box girders. So that means that the ruggedness of the installation is not as challenging as if it's exposed to the elements. So yeah, that is in our favor, and also it means that cabling is relatively straightforward as well with that environment, apart from the long distances involved. And yeah, so speaking of cabling, we actually just for this one span installed about 3 kilometers of cabling. It's collecting currently about 10,000 measurements per second from the system and streaming that up to our cloud platform via a cellular uplink. As we expand the project, we anticipate switching over to a fiber link for this, but the cellular link has been pretty up to scratch. So basically, our approach we've taken here is to have very sort of simple, stable software at the edge. Basically just responsible for compressing and queuing the data for publishing to the cloud platform, and all of the sort of business logic and analytics is occurring in the cloud, where it's a little bit more fault tolerant, I suppose. So we don't want to accidentally we don't want to have to be having like a lot of churn of the software at the edge if possible. So basically we're just passing the data directly to the cloud. And yeah, so some of the different processes we can apply here in this sort of scalable, modular, cloud-based platform, it's really limitless. what sort of processing modules you could use to transform those raw sensor measurements into useful features. But in our case, we're doing some time synchronization, some signal cleaning, some resampling for the purposes of like FFT, for example, some normalization of the strains, extracting some different sorts of features that are inputs to the later analysis, doing some fusion between correlated sensors, and also preparing for long-term data storage. So after this point, the data is sort of in a useful format for further analytics. Here, I'll just show you, I think a mantra I heard a few times in sessions yesterday was, seeing is believing. So the importance of visual explanation. Sorry, my headset turned off then. The importance of visual explanations for structural health monitoring events is quite important. So here you can see we've got a sensor in the road below the road deck around about here, and you could see that as the vehicles pass by, they've triggered the responses you would expect in that single accelerometer response there. So yeah, in terms of data management, we're effectively collecting and storing about 1 billion measurements per day. And we've so far collected 6 months of data since the instrumentation in June 2020. I won't go into a lot of detail about sort of the data management, apart from pointing out, that this is only 5% of the bridge that's been instrumented. It's a reasonably large amount of data that is streaming through the system. So a sort of tiered data storage approach is the most appropriate for long-term scalable performance. So for example, like the high resolution, high frequency raw sensor data is pertinent for real-time processing, but is not necessarily important to be like hotly available for long-term analysis, whereas the derived features we need to have available for the longer term. So at the moment, we're not intending to discard any information, but it was just a matter of trading off the latency for the performance. And here's just a quick little snapshot of some of the raw data from 6 of the accelerometers. This is just showing power, average acceleration, and max acceleration during 1 minute aggregates. So this is just a three-week sample from the bridge. You can see like the Monday to Friday peaks substantially different from the weekend activities. So these are 1 minute aggregates, probably aggregated up further for visualization purposes, but just sort of illustrate that idea that we're not going to be showing like 100 hertz signals over long periods like this. All right. And I think at this point, I'm going to hand over to Khoa, who will discuss the analysis and the damage identification techniques.
Thank you, Ben. Hi, everyone. So even though our talk today focused more on the system and platform side of the project, I also would like to introduce some of our effort in the analytics side of the project. So as we know that most
Sorry, I'm not hearing you, Khoa. Maybe it's my fault.
So I already, do you hear me?
Yes, I can hear you very well.
Okay, yeah, thanks. So most of the effort from the engineering side utilize the use of finite element modeling for damage detection, where the data from the model are compared with the sensing data for damage detection. However, the numerical model may not always available, or it may not adapt well to the change in environmental and operational conditions. So in our case, we focus more on the data-driven approach, which establish a model from data using machine learning techniques. And one of the issues in SSM is we normally do not have data associated with the damage condition of the structure. So we will focus more on the one class approach, where we only use the data from the healthy structure to build a benchmark model. And when new data comes in, it will compare against the model for Chen or damage detection. Next slide, please, Ben. So we work with UNSW to build some preliminary finite element model for the span we instrumented. So the result from the FEA model showing that one of the dominant frequencies, some of the dominant frequency are quite well aligned with the frequency obtained from the sensing data. So the next step is we need to use the sensing data to update or calibrate the model to reduce the discrepancy. Next step, next slide, please, Ben. We also analyze the data collected from accelerometer and the strain gauge in the span, and we can see from the left figure is shows some of the dominant frequency band for the external of the span, and here we use frequency domain decomposition to fill the sensor in one tunnel, and the top dominant frequency is less than 4 Hz, and it's well matched with some of the dominant frequency we survey in the similar long span box cluster bridge in other area. And we can also see, like in the right figure, is some of the strain data collected from section A of the span, and I think the data, the strain obtained from the sensor in different locations align well with our understanding on the expected behavior of the session under the light traffic. But here is some of our finding. We find that the share sensor have a clearer signal against traffic excitation compared with the bending strain gauge we instrument. Next slide, please, Ben. And as Ben already showed, our system, including data acquisition, data analytics, and a user dashboard, and we can see that the traffic behavior captured by our sensor, as shown in the video Ben show us, and based on the sensing data, we extract some damage sensitive feature and apply and use it to train both traditional and deep one class model for damage detection. And we can see in the middle figure that our machine learning model generates some structural health score indicating the structural damage of the position of measure. And we can see here, on the health score positive, indicating that the structure is healthy. And in the right figure is the our current dashboard for the system. And when the asset owner click on the area of interest, it will show the sensor network of that area. We can see here, like the tunnel that Ben showed last time. And when we click to a particular sensor, it will show the machine learning health score at that location. And when we click to the health score, it will show the raw data associated with the health score. So in case of there's some alert, the asset manager has some idea of what component of the raw data trigger the alert. Next slide, please, Ben. And this is another application which we stream our data from the platform to another project, which also a digital twin project, which CSIRO collaborate with the Queensland government to visualize some infrastructure asset. And here we can see that this is the span, the gateway bridge show in 3D, and beside the 3D information, we also streaming some data collected from our sensor. And we can see that here in the plot below the map, that this is the energy on the span generated by the acceleration. And it's clearly see that this energy capture the operational condition of the bridge, like it have high energy during daytime and low energy during nighttime. Next slide, please, Ben. Yeah, so this is the end of our talks. So in the next step, we would like to optimize our sensor network based on our proof of concept project, and we improve our data analytics and visualize platform we show, and yep, so and we'll scale the solution to the whole bridge. Thank you.
Thank you, Ben and Khoa. This is really a great presentation, and well done, and congratulations to CSIRO team. I think that's really impressive.
Thank you.
So let's probably have one question, because I'm just concerned about the time. We are going already in the break. Tea break. So any question for Ben and Khoa?
Yeah, I have a question if you have a time.
Yes, please. Yeah.
Said Mazaheri from Beta International Associates. That was very interesting presentation from Ben and Khoa. And actually, this is the area that we as an industry are working on it, for a long time. So I have two questions actually. First of all, it was impressive that the design life of that bridge was 300 years. So we rarely see a structure with a very long, design life span. My question is that Ben mentioned that they use 3 kilometers of cabling. And we know that all of these data and sensors are relying on those cabling. The first question is that what's the design life of that cabling, and how frequent we need to change it? This is one of the main questions within the industry. We have to take care of that, and I have been in these kind of challenges for many occasions. The other question is that, as Khoa mentioned, the finite element modeling when we implemented is not aligning with the actual data. So we need to adjust some sort of techniques in order to make it conforming with the data. And one of the techniques that these guys mentioned is machine learning, artificial neural networks whatsoever, like that. And these techniques are relying on the amount of the data that we measure and the criteria that the measuring replicates. So for example, if we got some sort of environment or other design condition that hasn't been captured by the data, the machine learning techniques is not capturing as well. So the question is that we need to update the machine learning techniques for all of the events which is not included during the data, and some of the extreme events which got the return, return occurrence, for example, every 10 years, 20 years, might not be captured. So this is one of the challenges for capturing the damages or diagnosing the problem that we need to address in the industry.
Ben, would you like to?
Ben and Khoa, do you want to answer?
Sure.
Answer the first question, Ben.
Sure. Sorry, I was trying to find the mute button. Yeah. So I noticed that Govinder's on the line. Perhaps he could add a little bit more to this, to be honest. But yeah, I think this is a pilot project at the moment. So but we did select high quality sensors, like pretty much the best quality we could get our hands on, and we've run all the cabling in conduiting. It's a benign environment with stable temperature and low moisture from what I mentioned earlier as well. So we have got a good environment for the longevity of the system, but it should be noted that there is definitely further redundancy and productionization that would go into scaling it up further. For example, redundant power or and communications. But yeah, as far as I'm aware, I wouldn't expect the sensor cables themselves to be the earliest point of failure. But I think the level of investment you put into needs to take into account the expected life cycle. And for our case, we don't expect to instrument this bridge for the next. We don't expect this span to last, for 10 or more years necessarily, as it's currently instrumented. And that discussion goes into the identifying the appropriate budget for the scaling up of the solution for that longer period. So yeah, I'm sorry I don't have any specific answers for how long that cable that will last, but it's something that needs to be considered for sure, because yeah, that 300-year design life was, I think, pretty phenomenal, and they had to achieve that for the new bridge. They needed to do a lot of novel techniques using stainless steel reinforcements, etc. And if you look at the two bridges, you'll see there's a lot more concrete at the base of the piers in the river as well. On the new bridge, I think they've put a lot more protection over that reinforcement. But yeah, definitely it's something that needs to be considered. And so nobody knows, or is willing to admit what the planned lifetime is for this particular bridge. But obviously that's something that you need to consider, because you want the SHM system to last as long as the bridge itself.
Thank you, Ben. Anything you want to add to that, Khoa?
Just for the second question. So even though our efforts mainly are about data driven, which we only use data to build our machine learning model, but we also work with the University of New South Wales to build the finite element modeling. So the idea, we want to use the model to simulate some damage or other scenario which we cannot collect it using the sensor in the normal bridge condition. So yeah, we know that we need to update the model using the sensing data, and I think there are a lot of literature on that, which people can use some technique like genetic algorithm or similar to calibrate the model against the new sensing data. So I think the interaction between the model and the machine learning is complement. The machine learning can adapt well in the changing in the operational or environment, but the model cannot learn the new information it not see. So why the finite element model can provide some scenario to validate the performance of machine learning, for example, some simulated damage or different operational condition which we cannot see in the normal operational traffic. So in the future, we also plan to use some cross test, which we use some vehicle with known mass to ride through the bridge and simulate some damage scenario as well, and yeah, to further validate our model. Thanks.
Excellent. Thank you very much. Thank you, Ben and Khoa. So there's other question, but if you have time, please look at the chat box and you can reply to some of the questions. So let's conclude our session this morning. I really want to thank all the speakers and also thank the audience for the discussion and the questions. So with that, I would like to hand over to Tommy if you have any thing before we go to break.